This is Professor Ramachandra from the Department of Physics, IIT Madras. I also belong to 2-3 centers. One is the Material Science Research Center, Nanofunctional Materials Technology Center, and Quantum Center for Diamond and Emergent Materials. As part of the Indo-French research program, we have the second project running between our group and the group of Professor Werner Paulus, who belongs to the University of Montpellier in France. So let me give you a brief introduction to what we have been doing all these years. I've had lots of collaborations with French universities, a lot of association with France itself since the last 3 decades, because I was a postdoc in CNRS Bellevue after my PhD. And since the last nearly 20 years, I've been associated with University of Montpellier, and before that University of Rennes, where Professor Werner Paulus has been a faculty. So we are very thankful to CEFIPRA for bringing scientists together from the French labs, French universities, to collaborate with us in Indian universities. So this has been a very fruitful type of collaboration, bringing forth scientists with different expertises to come together to work on topics, all kinds of topics, including the present day quantum materials, and to further our research in a way that only such collaborations will make it possible. So the first Indo-French project we had about 10 years back, Professor Werner Paulus, he's an expert in crystallography, in single crystal growth aspects, whereas we are thin film growers, so we work on strongly correlated oxide systems. All these oxide materials, when they're obtained in bulk form, we also get them in high quality thin film form, and we do all the characterization, optical, magnetic and electronic property studies. So my expertise with that of Professor Werner Paulus is very, very complementary in the sense of growing crystals there, and in our group growing high quality thin films and nanophases of oxide electronic materials. So in the first part of our project, the first project that we completed very successfully almost about a decade back, this was on calcium iron oxide, CaFeO3 and CaFeO 2.5, which is called a brown millerite compound. When you reduce calcium iron oxide from its perovskite form to O2.5, it becomes a brown millerite. The single crystals of these brown millerites were grown by Professor Werner Paulus's group, and we concentrated on preparing the nanoparticles of calcium iron oxide. One of the beautiful outcomes of this work was when CaFeO 2.5 was prepared in its nanoform. We also envisaged this before submitting the proposal. We felt that the oxygen diffusion would be much faster in the nanophase of calcium iron oxide. And indeed it was true. All our experiments, the 3 years of CEFIPRA project that resulted in 2-3 very good papers, also concluded with a note that indeed when you have nanophase, antiphase boundaries, they open up more number of oxide vacancies with which the diffusion, oxygen diffusion becomes much faster and at much lower temperatures. I think probably this is one of its first kind of works to show that in a brown millerite compound, oxygen diffusion could happen at a much lower temperature. Now, a couple of years later, we also organized an Indo-French workshop called, it's a joint project where the conference was held in University of Montpellier, where I took about 15 scientists from various universities, institutes, including Madras, And then there were about 15 people from the French side. We all sat together, 3 days of seminars, deliberations, and very fruitful exchange of ideas happened during that workshop. We'd like to do one more like that. So the second, the present project is on dealing with electronic correlations in quantum materials. That is mostly on iridates. These are wonderful systems to explore. All this, the genesis for this started with the work of a PhD student who worked on, one of the iridate oxides interfaced with manganite, insulating antiferromagnetic manganite. We found that there is an exchange of electronic exchange happening at the interface, exchange in terms of iridium ions and manganese 3+ and manganese 4+. This led us to the planning of the work on the present ongoing project, where Shreya is working on, is that we are exploring the possibility of looking at depositing strontium-based iridates to see the effect of charge transfer and the effect of lattice strain on all these correlated electronic correlations, including Rabi oscillations, including what happens if you are able to form a two-dimensional electron gas at the interface. And once you have a 2D electron gas at the interface, you could start seeing extremely interesting physical properties. Even though there was this huge problem of COVID for 1.5 years, still our work progressed, and very soon we'll be exchanging students from IIT Madras to University of Montpellier to try out some of the experiments there, and crystals grown in that lab will be brought here to do the experiments here. So in a nutshell, we are working on these new class of iridium based quantum materials. These are very important from the future point of view of making all oxide spintronic devices. Now spintronic devices are made of several different materials, but then our aim is to see the fabrication of spintronic devices based on all oxide systems.
Hi all, I am Shreya. We are working on strongly correlated quantum transport in spintronic heterostructures in collaboration with University of Montpellier from France. So here we are actually studying the spin transport using SR-IRO3 as the metallic layer, which has got high spin-orbit coupling, and SR-COO2.5 as the magnetic layer. So here we have optimized the deposition parameters for the bilayer system using the pulse laser deposition setup we have in our lab, and followed by that we have done the structural characterization of this bilayer system using the in-plane XRD, and using the electrical and magneto transport studies we have done using the physical property measurement system available in our lab. We could conclude that there is an interface charge transfer between iridium and cobalt ions, thus resulting in a two-dimensional electron gas formation at the interface. So from the results we obtained from these magnetoconductance measurements, we have seen that the inelastic and the spin orbit scattering lengths were coming in the order of nanometer, which was crucial for quantum nano spintronic device applications. So further characterizations like synchrotron facilities for confirming the charge transfer at the interface will be carried on with the collaborator from France. That will be going ahead in the proceeding months.
Long live India and France friendship.